Welcome to chapter 2, which is energy, energy transfer and general energy analysis. So the objectives, you can just go through the objectives. These are the objectives that will be you should be able to achieve at the end of this chapter. Yeah. So the first video will be covering 2.1 and 2.2, which is 2.1 is introduction. So if you take the entire room, including the air and refrigerator or a fan as a system, which is an adiabatic closed system, since the room is well sealed and well insulated, only energy interaction involved is electrical energy crossing the system boundary and entering room. Okay, so you remember in chapter 1, right? We were actually I was actually introducing you to so many concepts like closed system. So what is closed system? Closed system is actually something like this. It's all totally closed. No mass can go in, no mass can come out, only energy can transfer in and out. So if you read this sentence, the only energy that goes in is actually the electrical energy. And adiabatic, what does it mean in adiabatic? Adiabatic means there is no energy transfer, no heat transfer, no Q in, yeah, no Q out. Yeah, adiabatic, it's a closed adiabatic means that no heat transfer in and out, no in, no out. Yeah, that is an adiabatic process. So the heat is actually sealed inside. Okay, now boundary. So this is the boundary. Remember, these are the important things about chapter 1. Yeah, the terms that's used, you'll be reusing it in the other subsequent chapters. As a result, the conversion of electrical energy consumed by the device is to heat the the room temperature will slowly rise. Because of this electrical energy, what happens is that the room temperature will also slightly rise. Yeah, same goes to this fridge. If this fridge is kept in a well insulated room, where if there is adiabatic, it means there is no heat allowed in and out. Yeah, only electricity that's allowed through the electrical supply. So what will happen at the end of the day? The room will actually rise in the temperature itself. Yeah. Okay, next we'll be going to forms of energy. This is chapter 2.2. So energy can exist in numerous forms. This thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, nuclear, and the sum constitutes of total energy, which is E. So the form of energy, there's macroscopic form and microscopic form. What is macroscopic? Macroscopic is possessed by as a whole with respect to something outside the reference frame. Example, the kinetic and the potential energies. Whereas the microscopic is actually related to the molecular structure itself within the within the object itself, in among the molecules and also the atom. Yeah, most of the time we will never be able to see. Yeah, example is the internal energy. Now kinetic and potential, also known as mechanical energy. Like kinetic is due to the motion and potential is due to the elevation or height. Yeah, formula for kinetic is half mv square. Yeah, half mv square. And then suddenly you can see specific. Specific means is divided by mass. Yeah, specific means divided by mass. And then we have potential mg h. Some books say h, some books say z. Z is height, h, yeah, is the same. So total energy will be internal energy plus kinetic plus potential. Okay, you open it up, that's how it's being written. So whenever you see divided by mass, it means it is in the form of specific divided by mass. Yeah. Okay, then we have the mass flow rate. What is mass flow rate? You see m with a dot. Okay, rho is the the density, and v will be the volumetric flow rate. Okay, so we have rho AC, cross section of the pipe itself. Like example, if this pipe, this is the cross section, and then we have the velocity average. Okay, you multiply, you get the mass flow rate. Okay, so that's done. Now when you use the word rate means it's divided by time. Yeah, so you have energy flow rate, which is actually giving you as power. Okay, so there are some physical insight of your internal energy itself. So these are the movement in the internal energy. So we have sensible energy, portion of internal energy of a system associated with the kinetic energy of the molecules, and then we have the latent energy due to the phase change, and then we have the chemical energy due to the atomic bonds, and then we have the nuclear energy. This is more of the nuclear like the nucleus of the atom itself, like uranium, plutonium, and all those things. So this is how they move. You can just have a look at it. Okay, next would be static form of energy. You see, when an object not moving like water in a reservoir. Yeah, it's not moving, right? Water in the reservoir. Okay, this is the static form of energy. So when you have an opening here, then this is the dynamic form of energy. Yeah, dynamic means movement, static means stay put. Yeah, not moving. Okay, so we have two forms of energy interaction. One is the heat transfer and the other is work. Now remember, this is the most important part that you have to memorize. The difference between the heat transfer and work is that heat transfer is initiated by the temperature difference. I repeat, heat transfer is initiated by the temperature difference. Anything other than that is work. Okay, so we have the nuclear energy. We have two types, which is fission reactor and fusion. Fission reaction is when it breaks up into smaller component. That's fission. Fusion is when it joins together. Yeah, like example, you see there are two heliums, it becomes helium-3. Fusion is mostly that's happening in on the sun. Yeah, and fission will be similar to all the power plants that's being designed on Earth, and also weapons, nuclear weapons, yeah, using concept of fission. Okay, now next we'll be going into mechanical energy. So mechanical energy is your kinetic and potential energy, yeah, and also mechanical energy due to the fluid movement. Yeah, this is fluid movement. Okay, energy due to the fluid movement. Okay, we have pressure divided by density. Okay, so otherwise you know about your kinetic and your kinetic and your potential. Yeah, the only thing that's different here is the fluid, due to the fluid. Okay, so next, these are just some pictures to just illustrate how does a hydraulic turbine works. Yeah, water push in, the turbine will turn and generate electricity. This is conversion of one form of energy to the other form of energy. Okay, let's move on to an example before we sum up this subchapter. So a car that is powered by nuclear, an average car assumes 5 liters of gasoline a day, and the capacity of fuel tank is about 50 liters. Therefore, a car needs to be refueled once every 10 days. Also, the density of gasoline ranges from 0.68 to 0.78, and the lower heating value is about 44,000. Okay. Suppose all the problems associated with the radioactivity and waste disposal of the nuclear fuels are resolved. The car will be powered by uranium-235. If a new car comes equipped with 0.1 kilogram of nuclear, determine if this car will need refueling under average driving condition. So let's calculate. Yeah, okay, a car powered by nuclear comes equipped with the nuclear. Okay, that's the solution. Okay, gasoline is an incompressible substance with an average density of 0.75 kilogram per liter. So nuclear is completely converted to thermal energy. Yeah, so what we have here, we have the mass of gasoline, which is rho multiplied with the volume. So we get 3.75 kilogram per day. So noting the heating value of gasoline is actually 44,000. So you just need to multiply this both. So the heating value is actually 165 kilojoule per day. Okay, so you can actually that is the question actually, to calculate the heating value of the car. Okay, so with this I'm ending the first video. I will see you in the second video for chapter 2.